Welcome to the video on the concept of LC tank circuit and the analysis of LC oscillator. So first we will discuss about the operation of LC tank circuit. So in this diagram it will shows one capacitor and one inductor. So in this tank circuit the capacitor has some initial charge. The charge from plate A to B through the inductor. The charges from the plate A to plate B through the help of the inductor, and this causes a potential through the coil and produces an electromagnetic field. So we already know about the concepts of inductor and capacitor. So when this capacitor loses all the charges, the inductor maintains the current flow by pulling charge from plate A to plate B. Plate A loses charges while plate B acquires charges. When plate B becomes sufficiently positive, it repels further charges and the current will stop. Immediately, the inductor loses its electromagnetic field. Now the charges start flowing from plate B to plate A. Now the same concept will be repeat again. Again the capacitor loses its charge, but the inductor maintains the current in the reverse direction, that is plate B to plate A. Again A gets sufficiently positive and it repels flow of the charges from B to A. So the inductor loses its field and the charges start flowing from A to B. So this whole cycle will be repeated to allow current to flow in alternate directions through the tank circuit. So this is the simple concept of this L and C tank circuit. So this LC tank circuit which produces the oscillation. So the basic equation of LC tank circuit is given as F equal to 1 by 2 pi root of L into C. So this is the basic frequency of oscillation equation. And now we are going to discuss about the general form of LC oscillator. So what is the general equation of the LC oscillator? So now please see the diagram. With this help of this diagram we are going to derive the general equation of LC oscillator. So in this diagram it shows one amplifier and three components like Z1, Z2 and Z3. So here first equation, so here this Z1 and this input impedance HIE both are in parallel, and that two are series with this Z3, and Z2 is parallel with HIE, Z1 and Z3. So let me see the first equation. ZL equal to HIE parallel with Z1 plus this Z3 is is connected in series. So HIE parallel with Z1 plus Z3. So this is parallel with this Z2. Now I am going to write HIE parallel with Z1. That is what? A parallel B equal to A into B by A plus B. Just apply the same logic. Here HIE Z1 by HIE plus Z1. And Z2 is parallel with this Z3 plus Z1 HIE by Z1 plus HIE. Again I am going to write Z2 is parallel with this one. So Z2 into Z3 plus Z1 HIE by Z1 plus HIE divided by this Z2 plus Z3 plus this value. Now it's a very simple expression. Yes, we can do this cross multiplication and everything, and we can take LCM. So what will happen is, so finally we can get this kind of equation. Okay, so Z2 into Z3 into Z1 plus HIE, where HIE is nothing but as input impedance, plus Z1 HIE divided by Z2 Z3 into Z1 plus HIE plus Z1 into HIE. So now I'm going to take this is a normal multiplication. I am going to take this Z2 is common for all this equation. So Z2 will be taken outside. Z2 into Z3 plus Z1 HIE plus Z3 Z1 divided by, I can rearrange the equation. So I'm going to cross multiplication Z2 plus Z3 into Z1 plus HIE, that is A plus B. Yeah, one second. Yeah, yes, this multiplication we can get this equation. So now we can write the voltage feedback Vf with this help of this diagram. So the Vf can be given as V0 into Z1 is parallel with HIE by Z1 parallel with HIE plus Z3. Now the feedback factor beta, the beta is called as feedback factor or feedback ratio. The formula is beta equal to Vf by V0. Now I am going to substitute the value Vf value here, and already V0, this V0 will be there and this V0 will be there, and this V0 and this V0 must be cancelled to each other. We can get the equation as this type. Okay, so after simplification I can get the answer for this voltage gain is yeah, and after simplification I can get the beta value is equal to Z1 HIE by Z3 Z1 plus HIE into Z1 plus Z3. So now we can write the voltage gain equation AV. So the voltage gain, the open loop voltage gain can be given as minus HFE by HIE into ZL. So just write the HFE by HIE equation here, and now write the equation ZL equation, that is just now before we found it, right? So this is what the final ZL equation. So now you can substitute the same value here. So as per the Barkasian criterion, A beta is greater than or equal to 1. So thus the same equation equal to greater than or equal to 1. Now a simple modification, after a simple modification we can get the equation as, yes, this one, minus HFE into Z1 Z2 by Z3 Z1 plus Z2 Z1 plus HIE into Z1 plus Z2 plus Z3 is greater than or equal to 1. Okay, so now I am going to take this term into right hand side. So after taking this term into right hand side, you can get this equation. Finally I am going to move this equation to the right hand side. So I can get plus HFE Z1 Z2 plus Z3 Z1 plus Z2 Z1 plus HIE into Z1 plus Z2 plus Z3 equal to 0. So this is the final general form of LC oscillator equation. Okay, so this equation is also called as master equation. So please remember this equation, because by deriving the frequency of oscillation, for example for Colpit oscillator or Hartley oscillator or a clap oscillator, we should write this equation without any error, because this is the master equation. Okay, so in case it is a Colpit oscillator, means we have to substitute the values of Z1, Z2 and Z3. In case of Hartley oscillator, again we have to substitute the values, right? So for Hartley oscillator, we already know about the concept of Hartley oscillator. So we have two inductor plus one capacitor. So for Colpit oscillator we have two capacitor plus one inductor. For clap oscillator we have three capacitors with one inductor. So this is the very important equation for deriving the frequency of oscillation for the LC kind of oscillators. Thank you.